Hello, Math 95 students. We are looking at Chapter 13. Chapter 13 is about radical functions. So we're going to look at how to simplify radical expressions and how to solve radical equations. What is a radical? A radical is this symbol right here, this radical sign. It's like a check mark here and like a big divide by symbol with a check mark on it. All right, the thing that's inside of that radical symbol is called the radicand, and the small number right here inside the check mark is called the index. Here are some more examples of what a radical expression might look like, and other examples right here. All right, moving on. Evaluate the radicals. So how do we evaluate radicals? All right, what the index means, like that 3 right there, that 3 tells you you're looking for a number that when you have 3 of those numbers, the same number, multiplying together, you get what's under that radical. You get the radicand. So, like if it's -8, we're trying to figure out what 3 things multiplying together give you -8. And it would be -2, -2, and -2, right? -2 times -2 is +4, and then 4 times -2 is -8. So the cube root, this is called a cube root or a third root of -8, is -2. And then this index of 4 right here on the next one means what number that if you have 4 of those same numbers multiplying all together will give you 81. And it is 3 times 3 times 3 times 3. Right? Because 3 times 3 is 9, and that other 3 times 3 is 9, and so 9 times 9 is 81. Or you could think of it 3 times 3 is 9, times another 3 is 27, times another 3 is 81. Whichever way you think about it, you're still going to get 3 as the 4th root of 81. So you remember back in chapter 9 we talked about the perfect squares. Like the perfect squares would be 2, 4, 9, 16, 25, because each one of those has a perfect square root. Well, you can go to higher powers than just a square. An nth, if anything has a perfect nth root, is called a perfect nth power. So -8 is a perfect cube or a perfect third power because it has a whole number cube root. It has an integer cube root. All right, the number 81 is called a perfect fourth power because it has a whole number or an integer as its 4th root. All right, we can rewrite an exponent and a root as each other. You can do that by putting the index of the radical as the denominator of the exponent. Let me show you what I mean. Let's say you have the cube root of x. All right, you can rewrite that as x to the 1/3 power. So anytime you want to rewrite it, you can just take the index and rewrite it as the denominator of the exponent. So let's do that some more. Let's say we have the 5th root of a. How do we rewrite that? A to the 1/5. Let's say we have the cube root of y squared. Well, you keep the squared on the y, but you put the 3 under it. You put the 3 as the denominator. So if you have an exponent on whatever this thing is, that exponent is going to be the numerator, and the index of the radical is going to be the denominator. All right, let's say you had, let's just say the square root of x. What's the index now? If an index is not given, then it's understood. It's an understood invisible 2. Okay? So the index is not explicitly written there, but if it's not, it's understood to be a 2 as the index of the radical. So you just rewrite it as x to the 1/2. So if we have the square root of a, we write that as a to the 1/2. If we have the square root of y to the 5th, how do we rewrite that? Y to the 5 halves, or y to the 5 over 2. And you can go the other way with it too. Let's say if we have 5 to the 2/3 power, we can rewrite that as a radical. Whatever the denominator of the exponent is, that is the index of the radical. So it's the cube root of 5 squared. Or if we want to, we could rewrite it as the cube root of 25, because 5 squared is 25. So it's the same thing. Let's say we have x to the 1/2. Well, remember the 2, if the 2 is the index of the radical, then we actually don't write the 2 because it's understood. So you're just going to write it as the square root of x to the first power, and you don't have to write the first power because the first power is understood. All right, so what if you had y to the 3/4? How would you rewrite that? The 4th root of y cubed. Okay. Let me make one note here. There's a difference between this and this. Okay, this is not the same thing. On this left one, this 3 is written in a normal size font. It's not written in the small font inside that check mark. So this means 3, and since there's no operator, it means times the square root of x. This other one, since the 3 is small and it's written inside the check mark, this is the cube root of x, or the 3rd root of x. So the left one is 3 times the square root of x, and the right one is the cube root of x. They're not the same thing. So you just got to make sure you're distinguishing between whether this number is written large or a normal way and not inside the check mark, or whether the number is small and written inside the check mark. Example 4, how do we simplify radical expressions? Some of this you'll already be familiar with. But we simplify radical expressions by, we have to break it down, and we look for, since this is a square root, this means something that's multiplying with itself. So 2 of the same thing multiplying together, that would give you what's under that radical. So 200 does not have a perfect square root, but maybe it can break down to something that does. So 200 can break down to 100 times 2. And then 100 breaks down to 10 times 10. And you could break it down other ways, and then 10 breaks down to 5 times 2, and the other 10 breaks down to 5 times 2. So we look for 2 of a kind. We look for pairs. All right, and we have a pair of 5s. Right here and right here is a pair of 5s. So that means we have a 5 come out. We also have a pair of 2s. So that means a 2 also comes out. But then we have one extra 2 left underneath, so that extra 2 stays under the radical. So my answer here then, since I got a 5 that came out and a 2 that came out, the 5 and the 2 that came out are going to multiply together and become a 10. And I have one extra 2 left under the radical. So this is the simplified version of this. And they are equivalent. They're equal to the same thing. Let me show you another way you could think about it. Another way you could think about it is, you can say 200 breaks down to 100 times 2. And then you might recognize, well, 100 is already a perfect square root. A perfect square, because it has a perfect square root. What's the square root of 100? It's 10. So 10 comes out because of that. Because 10 is the square root of 100, and that extra 2 stays underneath the radical. So that's another way to do it. And I'm fine with whichever way you feel more comfortable with, whichever way you're better at. Okay. Now, when you have variables involved, there's a different way to think about this thing. You remember how we can rewrite the index as the denominator of the exponent? All right, so do it like this. Let me show you the long way to do it, and then I'll show you the short way to do it. X to the 7th is the same thing as x times x times x times x times x times x times x. I think that's 7 of them. So we're looking for, since our index is 2, a square root, we're looking for 2 of the same kind. So we got, that's a pair of x's, that's a pair of x's, that's a pair of x's, and that one extra x left underneath. So since this is a pair of x's, that comes out as an x. And since that's a pair of x's, that comes out as an x. Since that's a pair of x's, that comes out as an x. And since that x doesn't have a partner, it has to stay underneath the radical. And so the final answer here would be, since there's x times x all on the outside, that's the x cubed on the outside, and the extra x left on the inside. So this is the final answer. But there's a quicker way to do it. Like, what if this was x to the 100th? You wouldn't want to have to write 100 different x's down and circle all that stuff. So let's talk about a different, more efficient way to do it. All right, so the more efficient way to do it would be to say, all right, if I'm going to put a 2 in the denominator, I want the fraction to reduce. So 2 under a 7 won't reduce. So then I break it down and I say, what is the nearest number to 7 that 2 will go into? And I can't go over 7. So it'll be 6. So I'm just going to make this be x to the 6th. And then what's left over? If I want to make x to the 7th, x to the 6th times x to the 1st. So it's x to the 6th and x. All right, and then, since this is an understood 2 under this, on this index of this radical, I'm going to put a 2 under that 6. All right, and that will now come out. How does it come out? Well, what's 6 over 2 reduced to? It reduces to 3. So it comes out as x to the 3rd. And this x here is just going to stay under the radical. And that's the other way to do it. That's the same answer we got before. And it's probably an easier way to do it. Let's do the same thing we just did on number 1 and number 2 to number 3. All right, so we apply what we did on number 1 to the 12. So 12 is a number. We're going to break it down to its prime factorization. And we apply what we did to on number 2 to this w to the 11th. So let's do it. The 12 breaks down to, you could break it down multiple ways, but we could do 2 times 6 or 4 times 3. And then the 4 breaks down to 2 times 2. So we got a pair of 2's and an extra 3 left over. So that means I've got a 2 on the outside, and I've got a 3 still under the radical. Now look at the w to the 11th. The index of understood 2 here will not go into 11, so I break the w to the 11th down to the nearest thing that 2 will go into, which is w to the what? To the 10th, because 2 will go into 10. So it's w to the 10th, and then there's one more w to the 1st that's got to go with it to make w to the 11th. Then I'm going to put that 10 over 2, and it's going to come out. All right, so what is it when it comes out? It's w to the what? To the 5th, because 10 over 2 reduces to 5. And then there's this extra w that has to stay under the radical with that 3. So this is my answer. All right, we're going to do the exact same thing with these two problems. So 48, how do we break it down? We're trying to break it down to something that has 2 of the same number. So 48 can break down to 8 times 6. You can break it down other ways. The 8 breaks down to 2 times 4. The 4 breaks down to 2 times 2. The 6 breaks down to 2 times 3. Now we're looking for pairs. All right, we have a pair of 2's right here. And we have a pair of 2's right here. And we have this extra 3 left over. So my answer is going to be, that 2 comes out as a 2. that pair of 2's comes out as a 2. That pair of 2's comes out as a 2. So on the outside I've got a 2 and another 2, which means I've got 4 on the outside. And that 3 is left over, so the 3 is still inside. Now look at the x's. X to the 4th. The x to the 4th, I can already write a 2 under that 4 because 2 will already go into 4. So that's going to come out as a what? As x to the 2nd. All right, this y to the 13th, it's not going to be y to the 13th when I break it down because 2 won't go into 13. So I'm going to break it down to the nearest thing to 13. That 2 will go into, which is y to the 12th, and an extra y to go with it to make y to the 13th. Then I'm going to put the 2 under that 12 because that will reduce, and so that becomes a what when you bring it out? Y to the 6th. And you got this extra y left over that has to stay under the radical. So this is my final answer to that first one. All right, now let's do the second one. All right, this 5x plus 3, think of that as one thing because it's grouped together in the parentheses. It's this whole expression. Think of that as one entity, one thing. So remember the index is a 2 right here. 2 won't go into 9, so I'm going to break this down to 5x plus 3 to the 8th and an extra 5x plus 3. Because 5x plus 3 to the 8th times 5x plus 3 to the 1st becomes 5x plus 3 to the 9th. And I broke it down that way because 2 will go into 8. So that can come out, but that has to stay underneath. So my answer is 5x plus 3 to the what? To the 4th, because 8 over 2 reduces to 4. And I still have an extra 5x plus 3 left over under the radical. And so this is my final answer. All right, these are similar, but on all the previous examples of these, the index was always just a 2. It was understood to be a square root. Now we're going to deal with higher indexes, higher indices. So now instead of looking for 2 of the same thing, I now have to look for 3 of the same thing on this one, or 4 of the same thing on this one, and so on. So the 40 is going to break down to, how about 4 times 10? We could have also done other ways. The 4 breaks down to 2 times 2. The 10 breaks down to 2 times 5. And so we're looking for how many of the same thing? We're looking for 3 of the same thing. So do we have 3 of a kind? Yes, we do. 3 2's with an extra 5 left over. So that means I'm going to have a 2 on the outside and a 5 on the inside of this cube root. What about x to the 17th? The question you have to ask yourself is, will 3 go into 17? And it will not. So then you ask yourself, well, what's the nearest number to 17 that 3 will go into? I can't go over 17, so I have to take it down to what? X to the 15th, because 3 will go into 15. Let me write this a little neater. X to the 15th. And then what's left over to make x to the 17th? X to the 2nd. Then I am going to take that 3, and it's going to go under that 15. All right. And so now this will come out. How does it come out? Well, what's 15 over 3 reduced to? It reduces to 5, so it comes out as x to the 5th. But this x squared is left over, and it's still inside of that radical. So this is my final answer for number 1. Maybe you should go ahead and try to do number 2 on your own before we do it together. Okay, so the 80 will break down to, how about 8 times 10? And the 8 can break down to 2 times 4, and the 4 can break down to 2 times 2, and the 10 can break down to 2 times 5. So then I'm looking for how many of the same number. I'm looking for 4 of the same number this time because 4 is the index. I have 4 2's and an extra 5 left over. That means I'm on the outside of that radical, I'm going to have a 2. And on the inside of that radical, I'm going to have a 5. Now let's look at the x to the 20th. The x to the 20th can just stay at x to the 20th because 4 will already go into it. So I'm going to put the 4 under that 20, and that's going to come out as a what? X to the 5th. Okay? But the y to the 15th is not going to remain a y to the 15th. I'm going to break that down to the nearest number to 15 that 4 will go into. And you know I can't go over 15. So I'm going to make it be y to the 12th because that's the nearest number to 15 that 4 will go into. So it's y to the 12th and y to the what? What else do I need to go with the y to the 12th that would make y to the 15th? Y to the 3rd. Now, I take that 4, that index 4, and I put it under that y to the 12th. So now that y to the 12th is going to come out as a what? Y to the 3rd, because 12 over 4 reduces to 3. And the y to the 3rd, I won't do anything else, so it's just got to stay as it is under that radical. And this is my answer to that one. Okay, on number 3, again, the 2x plus 7, because it's grouped together in parentheses, think of that as one thing. So the 2x plus 7 to the 34th is one thing. So I'm going to break, the 5 won't go into 34, so I'm going to break it down to 2x plus 7 to the, what's the nearest thing to 34 that 5 will go into? It would be 30. And then what's left over, 2x plus 7 to the what would be needed to make the 34th power? It would be to the 4th. So then you put the 5 under that 30, and this will come out. So how does it come out? It comes out as 2x plus 7 to the what? To the 6th, because 30 over 5 reduces to 6. And then I have the 5th root of, this is still left under the radical, 2x plus 7 to the 4th. And that's my final answer for that one. All right, this next example is really, I think it's a little simpler than the rest. We're just evaluating this function. So f of x equals the cube root of 2x minus 1. And we're trying to do f of 14. That means we're just plugging 14 in for x. So it's the cube root of 2 times 14 minus 1, which is the cube root of 28 minus 1, which is the cube root of 27. Now, what is the cube root of 27? Maybe you already know it's 3, but if you didn't know it was 3, you just break the 27 down to 9 times 3, and the 9 breaks down to the 9. I'm running out of room here. And the 9 breaks down to 3 times 3, and we're looking for 3 of a kind, and we have 3 3's, and there's nothing else left over. So 3 comes out, and there's nothing under the radical, so it's just 3. All right, the next one is f of 6. So f of 6 will just be plugging in 6 for x, so it's the cube root of 2 times 6 minus 1, which is the cube root of 12 minus 1, which is the cube root of 11. And you can't break that down, so they're just going to have to leave it as the cube root of 11. And the next one, g of 16, so since g of x is this guy, I'm plugging in 16 for x there. So g of 16 means I plug in 16 for x. So negative 3 times the square root of 16 plus 7. So the square root of 16 is 4. So it's negative 3 times 4 plus 7. So that's just negative 12 plus 7, which is negative 5. So that should be the answer to that one. That is good enough for section 13.1. Good luck on that assignment. I'll see you again in 13.2.